Okay, welcome to the next lesson. This lesson is on changing the equilibrium, and it covers off the rest of specification reference 3.4.2. The learning objectives for this lesson are as follows. First one being to be able to predict the effects of changes of temperature on the value of the equilibrium constant. Remembering that the equilibrium constant is the ratio of concentrations of products to the concentrations of reactants at equilibrium. So what effect do changes of temperature have on that ratio, of the equilibrium constant? Also, we're going to want to understand that the value of the equilibrium constant is not affected by changes in either concentration or addition of a catalyst, only temperature. So firstly, we're going to look at the position of equilibrium and the changing of the position of equilibrium. So that's all about Le Chatelier's principle, of course, that we've learned before. So let's just recap Le Chatelier's principle. And that says that if there is a change in concentration or pressure or temperature, the equilibrium will move to help counteract the change. So let's just drill down on some of these terms to make sure we remember them. So the position of equilibrium, as in the title, and the equilibrium will move. Let's consider those two terms. First of all, position of equilibrium. All that we mean by position of equilibrium is the amount of products and reactants that are present at equilibrium. And so if that equilibrium is going to move, then the amount of products and reactants is also going to move. That is what moves. It's just the ratio of products to reactants going to change when the position of equilibrium changes. So that's what we mean. But before we move on, let's just recap a bit of terminology. And in order to do so, let's consider a standard equilibrium reaction with hydrogen gas reacting with iodine. And let's have that in the gas phase. That's going to be in equilibrium with 2 moles of hydrogen iodide gas. Okay, so at any one point you're going to have an equilibrium mixture that contains all of hydrogen iodide gas, iodine gas, and hydrogen gas, because that reaction doesn't go to completion. It is an equilibrium reaction instead. So when you hear questions or text talking about the equilibrium position has moved to the left, let's just make sure we're familiar with that term. So the equilibrium position has moved or will move to the left. What that means is that the backward reaction has been favored. Okay, so that's the same as saying backward reaction, i.e. the reaction that's going from right to left. Because we've got two reactions going on at the same time. So we'll write the backward reaction is favored. That's the same as saying that. And in terms of reactants and products, what that means is that you're going to have more reactants with this change in position of equilibrium, and therefore less products. So that's moving to the left. If the position of equilibrium is going to move to the right, then the opposite is going to be true. So in a different color, let's say, okay, if you see something that says move to the right, so that's from left to right, then that of course is going to be the same as saying the forward reaction is favored. And in terms of reactants and products, then of course you're going to have less reactants. They're going to react more. And when they react more, you're going to get more products. So that's what we mean by the position of equilibrium and the equilibrium moving either left or right to help counteract the change. So let's have a look at the effect of changing the temperature on the position of an equilibrium. So let's do it by means of a little table here. So let's say we've got in the first column, we've got external influence, which is going to be either increasing or decreasing the temperature. Then we want to consider what the equilibrium will want to do. What will it want to do? Let's ask ourselves that. And then lastly, let's consider how does it do that, it being the position of equilibrium. Okay, so if that's our three columns, let's consider first of all increasing the temperature. So if we increase the temperature, so we're adding heat, the equilibrium will actually want to remove or absorb that heat. And so, of course, all equilibrium reactions involve a change in enthalpy, all right? And so one way is going to be exothermic and one way is going to be endothermic. So if a reaction, an equilibrium situation wants to remove heat, then it's going to move in the endothermic direction. Okay, so there is our first option where we actually increase the temperature. So then we're going to consider if we decrease the temperature. So if we decrease the temperature, the equilibrium is going to want to replace that heat. It's going to want to replace that heat, and how will it do that? Well, it will then move in the exothermic direction. Move in the exothermic direction. There we have it. Okay, so let's just make sure we understand that by looking at a couple of examples. So let's have a look at example 1. Okay, so we're going to start off with some sulfur dioxide. And let's react that with some oxygen gas. And that's going to be in equilibrium with sulfur trioxide. Just balancing that, we're going to need 2 moles of sulfur dioxide and 2 moles of sulfur trioxide. So we have an equilibrium reaction there, and as it happens, the enthalpy change for that reaction is minus 197 kilojoules per mole. So first thing to notice is that the minus sign signifies an exothermic reaction, but we have two reactions going on here. We have a reaction making sulfur trioxide, that's the forward reaction, and we have another reaction going on exactly the same time where sulfur trioxide decomposes back into sulfur dioxide and oxygen. So the standard way of writing these enthalpy changes is that the enthalpy change that is listed always applies to the forward direction. So in this case, we can see that it is this reaction here that is the exothermic reaction. Okay, so let's consider that we increase the temperature. Okay, so if we increase the temperature in such an equilibrium, first thing we want to know is we want to know what is going to happen to the position of the equilibrium. Well, the equilibrium is going to move to the left, right, to absorb that heat, because we want to go in the endothermic direction, which is the backwards or the left direction. So that little symbol there can illustrate the fact that it's going to go in the endothermic direction to the left. Now, what effect is that going to have on the amount of reactants and products? Well, if it's going in the left direction, then that means there's going to be less product. And if there is less product, then what effect will that have on Kc, on the equilibrium constant? Let's consider that for a second. So first of all, we might want to write down what Kc is in this case. So Kc is going to be the concentration of the product, sulfur trioxide. And from the balanced equation, you see that there are 2 moles of sulfur trioxide. And there are 2 reactants. First of all, we have sulfur dioxide, 2 moles of that in the balanced equation. And we also have 1 mole of oxygen. So that's our Kc. And if we are getting less product, less sulfur trioxide, then you can see that Kc is going to decrease. So let me just cross out that question mark because we just worked that out. Kc is going to decrease. Good, there's example 1. Let's do another example to be complete. We'll do this one in green. So example 2 is a different equilibrium reaction. Instead, we have some methane. Let's have some methane, and we're going to have that in equilibrium with hydrogen. And we're going to make some ethene out of it. So we're making ethene and hydrogen out of methane. So we're going to need 2 moles of methane. We're going to get from that 3 moles of hydrogen gas and 1 mole of ethene. And that is a reaction that doesn't really want to happen. All right, so the endothermic reaction is quite significant. So it's an endothermic reaction in the forward direction of plus 377 kilojoules per mole. And in the same way, let's consider what would happen to that equilibrium situation if we increase the temperature. So again, we're going to increase the temperature, put a little semicolon in there. And are we going to favor the forward reaction or the backward reaction? Well, in this case, the forward reaction is endothermic. And so what we're going to do is we're going to favor the forward reaction. So let's just illustrate that with a symbol like that. Okay, so if we are favoring the forward reaction, the endothermic reaction in this case, then are we going to get less product or more product? Well, of course, we're going to get more product this time. All right, and lastly, let's consider what is going to be the effect on Kc. Now, we could write the equilibrium expression out. But I think you can just imagine it and see that Kc will also increase if the amount of product is going to increase. So that covers the change in the temperature effect of Kc. So let's consider the effect of changing the concentration on the position of the equilibrium. And let's bear in mind that the equilibrium constant, Kc, is fixed at a given temperature. So if the concentrations of one thing in the equilibrium mixture changes, then the concentrations of the others must change to keep the value of Kc the same. Let's illustrate that with an example. We've got some ethanoic acid. Let's start with some acid. Well, let's react that with some ethanol. That's going to be in equilibrium with its ester. And water is going to be the byproduct. So if you increase the concentration of the acid, if we're going to increase this, then the equilibrium position is going to move in this direction to make more products and get rid of the extra reactant that you've added. And it's going to do that such that the equilibrium constant stays the same. So as much as the numerator is changed, the denominator is changed in the same amount, so that Kc stays the same. Lastly, let's consider the effect of adding a catalyst on the position of equilibrium. And what we need to know is that catalysts have no effect on the position of the equilibrium or on the value of Kc. And this, of course, is because the catalyst will increase the rate of both the forward and the backward reactions by the same amount. So the equilibrium position stays the same as the uncatalyzed reaction, that is. But of course, the catalyst does speed up the reactions, both forward and backward, so the equilibrium position is reached quicker, but the same equilibrium position is reached in the end. So that completes the lesson on changing the equilibrium. Let's just check that we've covered off our lesson objectives. Are we now able to predict the effects of changes on temperature on the value of the equilibrium constant? I hope so. Increases and decreases in temperature depend on whether forward reaction is exothermic and endothermic. And then, of course, we want to understand that the value of the equilibrium constant is not affected by changes in either concentration or the addition of a catalyst. Okay, thanks. I hope that's helped, and see you in the next video.